a presentation that some of you might have seen before, but I thought it might be timely, and then I would run it by you again. So I'm going to talk about fire size. The Coarse-Filter argument is that if we use an understanding of historical conditions as guide for management, we're more likely to maintain a full range of ecological services. That's predicated on several assumptions, one of them being that the Coarse-Filter indicators are a true reflection of historic conditions, essentially that they're good indicators. So what's a good indicator? I always refer back to the SMART model: specific, measurable, assignable, realistic, and timely. So let's just go through one example of a Coarse-Filter indicator, and it's one that we all probably know well, which is the amount of residual vegetation left over inside a disturbance event. And we'll just run through this really quickly. In terms of specific, we believe that residual vegetation levels within harvesting events are inconsistent with natural ones, that there's not enough and there isn't enough variation, for example. Measurable, we can use a number of methods for measuring it. Quartiles, I'm just going to use quartiles in this example, and you can use that using high resolution imagery, field measurements, GIS exercise. The companies might want to measure this with regular audits from a regulator. The idea is that we want to approximate Mother Nature at fine scales, and you might want to measure and report that every 5 years or so, so you have enough variation. So here is NRV for the proportion of disturbance events in remnants, ranges from 10 up to almost 100 or 95%, and it's got a nice distribution, and the different colors there are quartiles. So then the next question would be, do we have any other reasons, cultural, economic, or ecological, to not adopt this distribution? And let's say for the sake of argument, the answer is no. So there's our indicator, there's our quartiles, here's how to measure it, and away we go. Nice, easy one. So for disturbance event size, we want to approximate fire sizes at meso-scales, and the idea being we want to get larger events, smaller events, and more variation. So same idea. So here's NRV for the percent of the area that's burned, and I'm just going to use Alberta for this example, but the distributions would be the same for Saskatchewan, Northwest Territories, Northeastern BC, very similar distributions. So not surprisingly, most of the area burned, over 80%, is in events that are larger than 10,000 hectares, and some of them over 100,000 hectares. So let's ask the same question in terms of our filtering process. Is there any cultural, economic, or ecological reasons to not adopt this distribution? And clearly there are, right? Where the social acceptability of 10,000 hectare clear cuts, or 20 or 30 or 40 or 100, isn't there yet. And ecologically, we're actually unsure of those impacts because there are going to be roads in there. And from a logistical perspective, it would take decades to harvest an area that size. So generally, across Canada, across the boreal, and I've just used BC and Ontario guidelines as examples here, there is an upper limit. In BC, the upper limit was 1,000 hectares, nothing larger than 1,000. In Ontario, under special circumstances, they could go up to 10,000 hectares. Quebec would be in the 10,000 hectare range as well. There's no jurisdiction I know of that allows events larger than 10,000 hectares. And of course, that is 80% of the area, accounts for 80% of the area that's burned. So what does that mean? So I've just mocked up a couple little toys here to show this visually. Here's an example of, a landscape, doesn't matter how big it is, and some wildfire events on there. And here's 15% disturbed by area. Now here is a limit of, let's say, 1,000 hectares, upper size limit of 1,000 hectares. It's also 15% disturbed by area. So the same in both of those slides, and here they are side by side. So when you compare some really simple metrics on this landscape, you can see, first of all, you're going to have more roads on the one in the left with the one with the threshold. When you buffer out, 100 meters, let's say, or 200 meters, the amount of area that's left as core, and that will be represented by the light green areas, you're going to have much more in the natural scenario. Sorry about that. You're going to have the opportunity for some very large patches on the one on the right, not so much on the one on the left. Okay, so that's the visual. In terms of the numbers to back that up, this is from work that I did years ago in northeastern BC, and it's from a landscape simulation model. So that top line in red there, those are the average set of results over 100 simulation runs, using the full historic range. And then the only thing I changed for the next set of 4 runs of 100 each is excuse me, the upper limit on the size of a disturbance event. So in this case, we have the total area that's in core forest, so that would be an interior forest, at 56% under an NRV scenario, and it drops by 10% as soon as you impose a limit, an upper limit of 10,000 hectares, from 56 to 46. And then you'll note actually it drops down a little bit more, but the biggest difference is just that 10,000 hectare limit, okay? The same thing happens in edge density, okay? We go from 29 and it jumps up to 34, and then it sort of flattens out, 37, 38, 37. So the surprising thing here was the huge impact of, a 10,000 hectare limit. We tend to think of that as that's a big event, right? But it's nowhere near the upper size limit of fires. So it does make a big difference. So what if we instead just started to cluster these patches? So we can still have an upper size limit of 1 or 3 or 10,000 hectares. We don't have to change that one. But what we don't have right now is the ability to create these large spaces where we don't have anything by clustering. Okay, so that's the only difference that we're talking about here, is just clustering disturbance events. So in this case, it's really interesting. What's happening here is that we're comparing a harvest event to a fire, and we're using that logic to get at this idea of approximating Mother Nature at intermediate scales. So maybe that's the wrong question. If we take a look at a comparison in time and space between NRV and CRV, which is the current range of variation, we have 2 significant gaps. One, we've already talked about. Greater than 10,000 hectares, the difference between that and up to 1 million hectares that Mother Nature can do, that's a pretty big gap. The other gap here is a time one. Even a 1 million hectare or 100,000 hectare fire, that can burn in a month or 2. That would take years to harvest. So we've got a time element to this as well as a space one. Okay, so maybe the better question is, there's a space-time footprint of harvesting events that's inconsistent with natural patterns. And so we would have to compare apples to apples to be able to do this. So we could use quartiles, we could use averages. So let's take a look at what that might look like. So let's put this in terms of what it might look like from a harvesting perspective. So this is northern Saskatchewan, and these are 10,000 hectare cells. I just randomly picked 10,000. They could be 20,000, they could be 5, could be 50,000. And in each one, I just added up in an average 20-year period how much of that cell burnt. And you can see here that it ranges from 0, and those are the ones that are the lightest shade. And as it increases and gets darker, these are the ones where it's more than 75% of those cells have burned in a single 20-year period. Okay, so there's an image of NRV right there, and that can be turned into a distribution. Okay, so the zeros, they're right here. Okay, 38% in a 20-year period didn't have any fire in them at all. Another looks like about 13%, greater than 80% of them burned in a 20-year period. So again, this is accumulation of fire activity in a 10,000 hectare cell. So it could be one fire, it could have been 10 different fires. It doesn't matter. It's the net sum of those that we're adding up here. So there is the distribution. That is NRV of our new indicator right there, from 0 up to 80. And we can chop those into quartiles. We can do anything we want with them. So here's back to my model again. So I've chopped this landscape up into 10,000 hectare pieces, and I've just used one piece of that indicator. So 51%, a little over half of those cells are undisturbed. All right, and that's Mother Nature. Now in this one, the toy model, again, where there was no control over clustering, that those 10,000 hectare events could go anywhere, only 4% of them were undisturbed. So just the difference between those two, 51% versus 4, we've got a pretty good indication that something, there's something that we could be working on. And a fire size or a fire event indicator will not pick this up. It'll say everything is just fine. So here's actually some real data from northeastern Alberta on the Al-Pac FMA. And in green is your NRV. So that's the same graph I showed you a couple of slides ago. So that's the natural pattern of clustering, lots of zeros here. And in this sort of pinky purplish, whatever you want to call it, color here, you can see that there's a lot in the 0 to 5, over half of the cells. None of them have 0. So we don't have any 10,000 hectare cells, and this is about a 300,000 hectare landscape. None of them have no disturbance, compared to 38 that would occur naturally. None of them have more than 40% disturbance on this end, whereas again, if you add up those bars, we would be at about 35 or 40% of them. So the clustering isn't happening. We're ending up doing a little bit of disturbance everywhere on the landscape. So again, this is a useful indicator that tells us the problem here isn't how much disturbance we have on the landscape, it's where it is and when we do it. So what's the new indicator? Well, we could use quartiles. There's certainly that's something that people are becoming more familiar with. But really, this is such an interesting scenario, because just by looking at the graphs and looking at these two extremes, the 0, the no disturbance and the high amount of disturbance, we're not creating those. So we could just focus on extremes as a beginning point, and we could probably learn a lot about our landscapes by doing that. And it's simple to understand, doesn't require a lot of statistics. So what does it look like on the ground? Well, what we did in our scenario is we assigned areas that we called wins and wheres. So the wins would be the zeros. They would be the areas where you don't want to have any disturbance activity. You don't want to have cultural activity. You want to, if there is activity in there, and you can see in these areas that they would have some linear features, that's where you might want to focus your restoration activities. And then where you are would be the areas that you would stay in for 10, 20, or 30 years. And that's where you would do forestry activity. That's where you would have, the focus of your installations in those areas for that time. So you can see that, it might not necessarily end up looking like a perfect grid system. That's just sort of a guide, this little image in the upper left-hand corner of how you might want to parse out your landscape. But you can see with the numbered and the numbers and the letters here, you can see how using this you start to control on an intermediate to fairly coarse scale where disturbance activities are in your landscape and where they're not. We don't have any control for that right now, and there aren't any other indicators that capture this. And if we don't have one, we will end up being everywhere all the time on landscapes and thinking that we're creating, otherwise very natural landscapes when in fact we're not.